Hi, now it's time to build up the constant current power supply which I've described in the previous two episodes. I've got it up here built on the breadboard, and we'll take a look at it in depth and we'll see if this thing actually works. I hope it does. I expect it to. And if not, well, I guess we'll have to fix it. I've got current and voltage pots here. These are only cheap crap single turn ones. I don't have any free 10 turn ones to hand, so these will do. Good enough for testing. I've got my constant current load over here, which you've seen described before. That'll help us test it. I've just got a resistor for a dummy load here, which we can attach and do some testing. I've got the LT3080 mounted on a heatsink here, which is the same heatsink I plan to use in my final design actually. And let's go. Let's see if this sucker actually works. And here's the circuit we'll be using today. It's pretty much identical to the whiteboard one that I've done in the last two videos. I've added a couple of things. I've added a limit LED on the output of the current limit comparator down here. So when the output of the current limiter goes high and turns on the transistor and goes into current limit mode, it also lights an LED so we can visually see. And if that happens really fast, then you'll should see some flicker on the LED there or something like that. I've added a 2.5 volt voltage reference, because a power supply is only as good as its voltage reference, because that's where additional noise will come from. That's where it gets its absolute values from. I've used an LT1009 here, slight overkill in this instance, but in the final design it's like a 0.2% 2.5 volt voltage reference, but it will allow us to drive the voltage reference input of a PIC microcontroller or something like that, which we can use for our digital panel metering, and we'll have to go into that in some further video. But today you can just use an LM336 or something like that. 2.5 volt voltage reference. We've got another dropper resistor in here to give our current range from 0 to 1 amp, and our voltage here, I've added some gain here with these two resistors. So our gain should, so our final voltage, that multiplies that 2.5 by a value of, that has a gain of 2.2, so that will be our maximum voltage output. And up here for our current shunt measurement, I've actually matched these 10k resistors here. So I've picked ones out of my bin and I've physically measured them on the multimeter and actually matched them so they're within, I don't know, I'm not sure what it was, but they were pretty close, sort of, you know, plus minus 2 least significant digits or something. So much better than the standard 1% tolerance, which is what these resistors are marked as. And the op amps we'll be using today are TLC 2272s. You could use a quad op amp, which is the 2274. This is just like a cheap sub 1 millivolt offset op amp. You could use like a, you know, a generic Jelly Bean LM324 or something like that. But realistically, when you're talking about the current shunt measurement up here, the voltage offset's probably going to be too high for that. So you want to use a semi-precision type device here, unless you want to tweak these values and put pots in and tweak it. Gets nasty. We don't want to do that. And we'll just go through the layout very quickly here. I've got my positive rail up the top here. I've got my negative rail all along the bottom, so all that bottom stuff is all ground. This is my voltage reference over here. This is my a constant current load, the LM334 here, and that's our current limiting transistor, and that's IC1 and that's IC2, and that's our current shunt resistor there. It's only a quarter watt, 1 ohm, so I don't have a 1 watt or 3 watt version. I have to go to JCar quickly to pick up a higher wattage one to measure some higher power stuff. But there's our output caps, and there's our cap which bypasses the adjust pin on the LM3080, and well, that's about it really. Bypass capacitors on the ICs there, input bypassing on the LM3080, and that's about all. We've got our output LED here for the current limit, so that should light up, and well, let's power this thing up and see how she goes. Alright, let's power this thing up. I've got it powered from about 8 volts from an external supply over here, because we're only going for a 5.5 volts or thereabout output range today, so let's flick it on and see what we get. Our meter over here, this is the output voltage. We've got nothing. Oh, our current limit LED's on. Let's, yeah, the current limit's all the way down, that's why. So if we turn our current limit up, let's turn current limit up to maximum so we don't muck around. Our output voltage is 5.5 volts. Yeah, that's because the voltage adjust pot is at maximum. It seems to be working. I've got my constant current load set to minimum down here, so it shouldn't be doing anything, much if anything. And what do we go down to? Oh, hey, we go down to 0 volts. What do you know? And there we go. That appears to be working just fine. I like it. I'm surprised that it does actually go down to 0 there. I think our constant current load could have something to do with that. So let's turn it up. I'm drawing 60 milliamps. Let's say draw 100 milliamps out of this thing. There we go, 100 milliamps. And let's adjust that voltage down again and see what happens here. We've still got, no, it's still going to allow us to go down to 0 there. I'm going to disconnect this constant current load, and without the load on there, it only goes down to 0.7 volts, and that's pretty much what I expected. Perfect. And let's actually remove that LM334 current source and see what we get at the minimum. There we go. It only goes down, without that 1 milliamp current source, it only goes down to 1.59 volts. That's because there's no load at all on the output except the multimeter, which is a 10 megohm input impedance. Now let's check the output on the scope to see if it's clean, to see if it's oscillating or not. I've got set to 1 volt per division. We've got our maximum 5.5 volts output, and let's wind that down, and I don't see any resemblance of any oscillation at anything during that range. Once again, we've got just the minimum load there. There's the 0.7 volts minimum. But let's switch that to AC coupling on the input so that we can see, wind it right down to 10 millivolts per division, and as you can see, it's nice and clean. Okay, so this is the output noise here. As you can see, 10 millivolts per division. No problems whatsoever. If we wind it right up, of course, the bandwidth of the scope, it just gets noisier and noisier. And I haven't probed it, you know, it's a breadboard, so we're just getting ballpark sort of noise figures here, and that's at minimum voltage. Okay, that's at minimum output voltage, minimum load. Let's go maximum output voltage, minimum load. There it is there. No problems at all. And it jumps around, of course, because it's AC coupling. So you'd expect it to jump around until it settles through the AC coupling input cap. And I like that. No complaints at all. It looks very clean, as you'd expect from a linear voltage regulator with a rated 40 microvolts output noise. In fact, I don't have the gear to measure 40 microvolts output noise. I'd have to roll my own amp and do all sorts of other things, and God, too hard. And if you actually want to see the difference, okay, I'm probing the output at the moment. We're at 10 millivolts per division. Let me probe the ground. So I'm leaving the ground hooked up, but I'm now probing the ground of the circuit. As you can see, virtually no difference, as you'd expect with 40 microvolts output noise RMS. Now let's do the same thing again at 250 milliamps, because that's, in theory, the limit of our quarter watt resistor there. We'll now be dissipating a quarter watt in that 1 ohm current sense resistor. I don't want to go over that until I get a bigger current sense resistor. So we're drawing 250 milliamps and measuring the output noise. Again, let's go down to minimum. There you go, even down at 0.0. This is our output voltage, of course, and no problems whatsoever. And let's go right up to our 5.5 volts. No, it's perfect. It's working exactly as I expected in terms of output voltage regulation. I like it. Okay, now we'll check our basic current limit. Up until now, we've had our current limit up on maximum, and we've had our, well, let's set our, the way we're going to test that is to set our output voltage to maximum. We're getting our 5.5 volts out, and let's wind. We're drawing 250 milliamps constant current on the output, and let's wind our pot down until we start. We should, if it enters current limit, we should see that lead turn on and this start to drop as soon as we reach the limit. Turn it down, come on. Right, there we go. Just the point it starts to drop out. Now, if we measure the voltage on that pot, it should be 250 millivolts, because if you look at our circuit here, here we go, if I get it in here, our current adjust pot down here, to have our current limit at 250 milliamps, we expect 250 millivolts on that pot there, which sets the threshold where it goes into current limit mode. So if I measure the center point of that pot, it should measure just either on or slightly over 250 millivolts. 262, bang. And when we turn it down, it's got to 253. There's a bit of error there. It started to go into current limit mode. Got a little bit of error there, but basically it's working. So let's set this to 100. I'm not looking at the other one, and we should be pretty close to 100 down here, and we are. You know, there's going to be some error here. You know, 50 milliamps, 55. These basically should match, and they do. So constant current limiting is working. Okay, now what I'm doing is going to probe the output pin 7 here of our current sense amp, and let's have a look at what that's doing when it enters current current limit mode. I've got it set to 1 volt per division here, and of course it's not doing anything at the moment because it's not actually current limiting. But if we turn this pot down slightly, it'll enter. Way, there we go, bang. It's just looks like it's jumped from there up to just under a volt. 0.8 volts, and let's continue to turn that pot down and lower the current, and yeah, as you lower it, it looks like it's going up, and that's why our LED doesn't turn on, because there's not enough voltage to switch on the LED. Only when it gets to only when it gets to about 2 volts is it going to turn on our LED there. Now, clearly what you're seeing here is this, although it's still acting like a comparator, it's doing the job of a comparator, it's not strictly just going between 1 and 0 in the output. That's because it's in the feedback loop here via the current limit transistor, via the LT3080, via the current sense. It's all happening all in real time, and it's working in a linear type region now in the feedback configuration. Now, if we actually disconnect the transistor from here and actually remove the loop there, the control loop, then we'll find that this device will actually switch like a comparator, as you'd expect when we adjust the control pot. So this is with the transistor in place. It jumps up to there, and then it does, that's where it entered current limit, bang, and then it works in a linear type region from then on. And if we disconnect the base of that transistor, gone. There we go, but we're still measuring the output, bang, our LED is on, and it switches, bang, like a true comparator, because there's no feedback happening there. So clearly, just trying to put the LED on the output of that comparator is not a good idea. It's not going to work. We need some sort of other mechanism to keep that LED on when it enters constant current mode. Now, you might think that the solution to this current limit LED is easy. We've got a spare op amp here. Why not just parallel these inputs up here, get rid of the feedback loop there, and put the LED straight on the output like that? Well, if you do that, it's going to be a problem, and I'll show you why. Now, if we go into current limit mode here, so when it drops 250, watch the LED here. And bang, see, it flashed on for a second, so it worked for a split second, but you continue, it's in current limit mode, but the LED's not on. And it really only comes on when you get right down in the noise down in there. And the reason for that is because the input is so, these inputs are so marginal. Of course they're going to actually be equal, very close to equal, because that's the idea of the current limit loop, is that it makes, you know, the output voltage of this exactly the same as the set current here by way of that loop. And if they're exactly like that, then, well, it's you know, it's going to be hit or miss. Whether it works, it depends on slight offset voltages and things inside the op amp. It's bad design, so we need another method. And as usual, the solution's pretty simple. All we want to do is just change the margin on this input just a smidge. So what we want to do is lower the voltage on this non-inverting input just a tiny little fraction compared to what it is to the loop over here, so that when we adjust this pot down and it gets just on the current limit, there's going to be some margin on these pins, and this LED is going to switch on. So this input, instead of being exactly the same as this input and having no margin, the non-inverting input will be slightly lower than this one up here. So when the pot gets just right on the margin, bang, it'll switch on. Now I've used a 10k and a 2 meg 2 here. That'll give us about 4.5 millivolts margin at the full scale volt input, and when you get lower, you know, down at 0.1 volts, it's only 450 microvolts or something like that, but it's just going to give it enough. So let's try that out. I've added the 10k in there, coming back into the op amp. I've added the extra 2 meg 2 going to ground there, and well, let's try it. Let's get down to our margin here and watch. This is our current limit. This is the output of our op amp, of our current loop op amp, and watch the LED. Watch the LED. It'll just switches on. We're not quite in current limit mode yet. Bang! So it's just on the margin. But check this out. It's not perfect. If we wind it down, it will actually go off because there's probably some noise on there which is causing us an issue, and then it comes back on solid right down at the lower end of the scale. So we're going to have to fix that one as well. So let's replace that with a 470k and see if that's any better. Let's try it out. Yep, I like that. 470k it is. And of course you can take that current limit output off to a digital digital input to your controller if you have one. But of course, if you have an intelligent controller and you're not using pots like we are here today to adjust the voltage and current, and you're using a digital controller like a PIC or an Atmel or something else to actually generate the voltages to drive the voltage and current, it knows what voltage and current it's driving at, and you would of course read the output voltage back off, and you'd read the output current back off as well, both of those. Then the microcontroller knows you don't need any of this current limit. It knows that the output voltage has not matched what it's set, so therefore it must be in current limit mode or vice versa. It just knows all of those values, so it can figure it out itself quite easily. And we'll just check that our LM334 is actually 1 milliamp, and it is with our 68 ohm sense resistor there, so not a problem. Let's just check that over the whole output voltage range. That's our output voltage there, and it's still sticking with 1 milliamp. And let's drop it down, and you know it's only going to go down to about 0.9 before it, yeah, there we go, it's starting to muck up now. And the good thing is that it's still drawing that half. You remember from the data sheet from the previous blog, we thought that it would get down to about, it'd still be drawing half a milliamp at about 0.8 volts or thereabouts, I think we said. And I just wanted to point out that up until now, my output capacitance here, although the data sheet says 2.2 microfarads minimum to make it stable, I'm only actually using 1 microfarad. I'm not even using a ceramic either as recommended. So it's because I don't actually have a nominal 2.2 microfarad ceramic to hand, so it's just fine with that output capacitance, and we can add some more later and stuff like that, and we'll play around with that. But no, it seems to be quite good, and let's actually remove the output capacitance altogether and see what happens. Okay, that's with no output capacitance at around about 2 volts, and as you can see, it's a lot noisier than what we were getting before. And let me put on a 0.47. Bang. And we'll just go down to our 10 millivolts per division AC coupled. That's with the 0.47 microfarad bypass cap on there. By the way, this is at 0.2 amps load. By the way, I am driving 200 milliamps. So let's remove it and bang, there you go. It does. That's with no output capacitance. It really does not like that at all, as you'd expect for a low dropout voltage regulator like this. So it seems to be stable, but you know, at high you'd have to test it at higher current. But of course you wouldn't. Just as good design practice, put in anything less than the recommended 2.2 microfarad ceramic output capacitance. But even with 0.47, seems to work fine at about a quarter of an amp. Okay, let's test the dropout voltage at no load. So there's no load on the output. The output voltage is at maximum at 5.5. Let's tweak it down to, if we can, to 5.50, just as a nice round number. It's a bit hard with these single turn pots, really dicky. That's why you need a 10-turn pot. Let me tell you, any good lab power supply should have 10-turn pot. I breathe on that. Fart halfway across the room and that thing's going to change. Okay, now this is our input voltage, this is our output voltage. The green is the input voltage here on the scope. The yellow is the output voltage down there. The ground reference is right on the bottom graticule down there. And let's wind the input down until we start either seeing, well, we probably won't see it oscillate, but until we start seeing that drop there. Oh, is that it? Yep, there we go. So, whoa, so we're talking 1.25 volts or thereabouts dropout voltage at no load. And if you're curious to see the dropout voltage at an amp here, this is our input voltage. I'm probing that directly on the input pin of the LT3080. So that's bypassing all the wiring on the breadboard and stuff like that. And I'm measuring the output directly on the pin as well. And that's still the output noise there. So let's wind the input down and see where the output starts to drop. There we go, around about 6.8 volts by the looks of it. Yep, about 6.85, 6.9 volts. So that's about 1.35 to 1.4 volts dropout voltage. And is that what we expect? Well, let's have a look here at the dropout voltage minimum, because the V control pin, remember, it's not the quoted specs because we've tied the V control pin and V in pin together. And sure enough, at an amp up here at junction temperature, well, we're going to be above 25 degrees. Let's go up to 50 degrees. You know, we're about 1.4 volts. So, yep, it pretty much agrees with the data sheet, as you'd expect. Now, one thing we really want to check is the power up performance of this, because the power up performance of any bench power supply is very important. You don't want it to overshoot. If you've got your output voltage set to 5 volts, you don't want a big spike like that and then it to, you know, level back down at 5 volts. You want it to ramp up nicely and then go rock steady at 5 volts. Now, let's have a look here and try and predict what's actually going to happen here. Now, the input voltage up here is pretty much, technically it's going through an RC filter here with the current shunt resistor, but it's negligible, really. So it's so the voltage is going to go straight through to power the LT3080 straight to the output. There's no capacitance around our voltage adjust pot or anything like that, or our voltage reference. So that's going to power straight up instantly, power the pot instantly. This op amp's going to turn on instantly, and it's going to try and drive the set pin of the LT3080 instantly, assuming our constant current control is set all the way to maximum, of course. Now, but we've got this massive 22 microfarad here with these with this 2K series resistance here total, because remember that transistor is not going to switch on during unless there's current limit, so that basically does not exist. So our turn on RC time constant is going to be there, these two series resistors plus this cap. We're going to see this thing ramp up and go to the output. But because that's actually in an active feedback loop and we're actually driving this with an op amp, it's going to actually charge faster than our, if we set our output voltage to a volt, then it's going to charge up much faster than you'd expect based on that RC time constant. So let's power this thing up and actually capture that on the digital scope and see if that's confirmed. Now what I've got here is the yellow trace here is the output voltage, and I've set that to 5 volts, and we're at 1 volt per division, as you can see, spot on 5 volts. And the green trace here is actually the output from the op amp here, pin 7, that actually drives that. And as you can see, it's significantly higher. And the reason for that is fairly obvious. Not only do we have the 10 microamps current flowing through there, which will give us a slight drop across there, but we've also, these values here, the feedback resistor and the gain setting resistors here, are fairly low value compared to these. So there's going to be some output current flowing through there and some drop across there. But because the feedback tap is there, it takes care of any extra current flowing through there. That's why there's that difference. So we're going to have a look at these, and we're going to capture these 2 points when the circuit powers on. I've got it into no load, so this will just be switching on into no load with, say, a 7.5 or 8 volt input voltage. So to do that, we're going to set our trigger point to about 1 volt there. We're going to have it on the positive edge. We're triggering off channel 1, which is our output voltage. So on the rising edge, as soon as it gets to 1 volt, we're going to trigger that. Let's set it to 50 milliseconds per division or so. Let's switch the voltage off. Let's trigger that, put it into single shot mode, and let's give it a go. Here we go. Bang! I switched the power on, and you can see it ramp up. Whoa, what's that down there? That's interesting. And you can see the output of the op amp go up like that and then come back down when it starts to regulate like that. And that's a very clean response. I like it. There's no overshoot or anything. We'll have a look at this thing down here later, but basically all we care about with switching on power supply is that it ramps up cleanly and doesn't overshoot. And this one doesn't overshoot at all. It ramps up like that, almost linearly, and then it clamps into voltage regulation like that. Our op amp response, of course, it's got to do things because it's an active loop there and it's trying to stabilize itself, and it comes down like that. Now, this looks kind of linear, but it's not. That's actually going to be the exponential curve caused by this RC here, but it's but you'll find that its time constant is going to be a lot faster than if what you'd expect from 0 if you do the math from 0 to 5 volts. And why is it going to be quicker? Well, that's a good question. Is because it is not power. It's not going to be 5 volts here instantly. This op amp is going to be higher than that, and as you can see, the op amp right there suddenly went wham right up to there and then started to go up like that. So that's going to affect the output voltage is higher than 5 volts there, so it's going to charge that capacitor quicker than what you'd expect. And if we lower the output voltage, I think we'll find that that will look even more linear because you're right down in this curve there. So let's give that a go. All right, I've set my output voltage at 1 volt. So let's do 200 millivolts per division, so that will end up ramping up to the same value there, but I think you'll find it's going to be pretty linear. Let's capture that again, single shot mode, and whoop, we're ready to go. Here we go. Bang, there it is there. And we can actually see that if we zoom in on that, yeah, look, that looks linear, but that is actually the start of the exponential RC curve. It's because that active op amp there is driving it faster than a normal RC curve. Now this little bit here is interesting. What's that? That's 200, 400, 600, 700 millivolts. Aha! That 700 millivolts happens to be the same as what our regulator is capable of going down to with no load. So there's some turn-on mechanism there internally to the LT3080 device that causes that sort of jump up there and then flat for a little bit. But if you followed that curve down there, I think you'll find that that will intersect precisely down the bottom like that. So it's got this little knee characteristic switch on like that, but it's not a problem because it doesn't overshoot because our output voltage is 1 volt and there's no there's a tiny little bit of overshoot in there. There's not, it's nothing to worry about at all. So it's nice and clean turn on, really. I don't mind that at all. Now I've switched it back to 5 volts output voltage here, exactly what we were getting before, and just to demonstrate, we'll see if we can demonstrate that faster ramp up time due to the op amp there. What I'm going to do is I'm going to temporarily move this sense point back to here and then power it up and see what we get. And I think you'll find that the time constant will be longer and match the math exactly for 1K and 22 microfarads. Alright, let's give it a go. I'm exactly the same time base, so I've got my power switched off. Let's single shot that and let's turn it on. Bang! There we go. And you can see that the output of the op amp is just switched on instantly like that, as you'd expect, because there's no RC time constant in the feedback loop anymore. So it just bang, due to op amp action, this output here instantly becomes this input here, so it ramps up to there and bang, 5 volts, and this is your RC time constant. But you've still got this little knee here due to the, that's probably due to the constant current source in there, perhaps, something like that. So that's still causing that little knee, but as you can see, the RC time constant changed. That was so much fun. Let's do it one more time backwards. We'll switch it off, go into single shot mode, switch it back on, and bang, there we go. Much faster rise time, but still that exponential curve. As you can see, the slight curve in there, and the op amp, of course, has to compensate for it all now, hence all that crap in there. And you can see that the output of the op amp rings a little once it hits that point, and it goes bang straight down. There's a little bit of undershoot and recovery there, and but I like it. Power's on cleanly as far as I'm concerned. Now I know what you're thinking. 22 mic, do we need it that high? What if we change it to like 100N? Because we do need some capacitance on there just to lower the output noise, and we'll need it for our current limit, as well as we'll probably find out in some further testing. But let's lower that to 100N, see what happens at switch on. So let's take out the 22 and we'll put in the 0.1 mic in there, and that should work a treat. Let's see what happens when we switch it on. Alright, I'm going to keep the same time base there as we had before, 20 milliseconds per division. Let's go into single shot mode. Let's switch this sucker on, and I think it'll turn on. Well, it definitely will turn on much quicker. Bang! Look at that. Woohoo! Check out the ring in on the op amp. It's trying to recover there, but the switch on is actually quite clean. Still very little overshoot there, and that's a 5 volt output. But there is, it's not as nice. I don't like it. I don't like all that ringing and all that decay on the op amp like that. I think I much preferred the, it was a bit smoother with the 22 mic, but that's 100N for you. Now it might be tempting to use that 0.1 mic there and have a faster switch on. Who cares what the op amp's doing? The output, it's not too bad at all. Well, let's try to see what happens in current limit mode. And to capture that, we'll change our trigger to up just below the 5 volt level there, and we'll trigger on the negative slope, because when it goes into constant current mode, the output voltage is going to fall. And well, let's try that and see what we get. I've put the 22 microfarad back in, so this is our normal circuit configuration now. Alright, we'll see if we can capture it going into constant current mode. Now, we're exactly the same as before. The yellow is the output voltage at 5 volts, and the green is the output of our control op amp. Now, I'm going to turn the current pot down so that well, let's go into single shot mode. Okay, I'll set my trigger below there, and I'm going to turn my current pot down. I've got no load, but it will actually switch on right down at the low end when it hits 0. Bang! There it is. And you can see the exponential discharge due to, you guessed it, this resistor R2 here, because when it goes into constant current mode like that, bang, it switches on this transistor, which then discharges this 22 microfarad cap through that 1K to ground. And that's taking about 10, 20, 30, 40, 50 milliseconds or so there to switch that off. So we can actually tweak the value of that 1K. You wouldn't want it any higher, but we could certainly lower that almost down to, well, effectively down to 0, so that we can short out the cap directly and get that fast turn on. But it seems very well behaved in current, in switch over to constant current mode. So let's try that again, but this time I've got a 1 volt output, so I've changed my volts per division and my trigger point, and we've got driving 100 milliamps into a load. So let's turn our constant current pot, and bang, that's what we get. But you'll find, I think, that wiggle in there was me turning the pot. Let's see if I can do it a bit quicker. So let's try it again. Single shot, bang, there we go. And let's do it slowly again. Here we go, bang, and yeah, that's me actually turning the pot there. So, bang, that's as fast as I can turn it, pretty much. And you see the op amps doing some business there, but the output just drops very smoothly and very cleanly. Alright, I've changed R2 there to 100 ohms, dropped it by an order of magnitude, and let's see what we get. And once again, you can see the op amp oscillating in there, and if we actually zoom right in on that, you can see that it is actually oscillating like that, doing its thing, but that doesn't manifest itself on our output here. Our output is dropping very smoothly because we've got the 22 mic cap on there. But let's drop that capacitor, as we mentioned way back, down to 100N, and see if we get a similar response. So we now have a 100R in there with a 100N in there, where we're 1 volt output with a 100 milliamp load, and let's give that a go. Let's go into constant current mode, turn our pot, bang. And this is rather interesting. Look, that the output voltage, the yellow trace, looks fairly clean, but when we zoom in, it goes up, and you can see that there's noise following in there like that. And I think that is possibly because we're in high res mode. So let's actually switch off high res mode, and we'll try that one more time. Bang, there we go. It's exactly the same. So that is a disadvantage. You can see the rolling average done in high res mode on the scope. Bit of a trap for young players, that one. Now I'll put my 22 microfarads back in, and let's give that a go. Bang, look at that. See? So it is much cleaner response with the 22 microfarads. And you can see that live here too with the 100N. There it is. As I turn it down, bang, look at that. Terrible. And with no capacitor at all, by the way. It's an absolute shocker. You don't even want to go there. So I'll put that 22 mic back in. Bang. Clean as a whistle. Look at that. And there you go. Not a problem. And I've put it to AC coupling, 10 millivolts per division, and that's the noise. If I adjust it, I'm adjusting the pot there. So you see the AC, that's in voltage mode, and we'll switch to current mode. Bang. Exactly the same noise. Alright, we'll measure the switch off transient now. I'll set up a current for 250 milliamps. There we go, we've got 250 milliamps running on there. And this is our output, AC coupled 50 millivolts per division. And the green trace again is our control op amp output. So let's trigger that and just disconnect the load. I know this isn't ideal, normally you'd electronic switch this, but we'll just disconnect that real quick, and bam, there it is. And you can see how it's immediately switched off there. There's a bit of high frequency stuff there, as you'd expect, and then it boop, ramps back down, and then it kicks in, and the op amp kicks in and controls it all, and all settles back down nicely. But that's 50 millivolts per division, so That's only jumped 50 millivolts there for a quarter of an amp output current. And of course that's with our 1 microfarad output capacitance. Let's change that. Let's actually add some extra capacitance in there. I'll get an extra 47 microfarads and I'll whack that on the output and see what difference that makes. Here we go. Didn't even trigger. There we go. Looks like we have to lower our trigger there. Let's try it again. And bang, there we go. Much smaller output transient this time because we've got greater output capacitance. But as I mentioned in the previous video, it's a bit of a trade-off. You can't have an infinite amount of output capacitance because then when it switches into constant current mode, all that energy from the output capacitance can be dumped into the load before it has time to regulate the current. So probably not a good idea. And we'll check the load when we do the switch on transient. So we want to set our trigger signal below like that. So because we expect it to droop down like that, 50 millivolts per division. So let's set it down there and let's disconnect our load, and here we go. We're going to connect our load real quick, and bang, there we go. There's our switch on transient, 100 millivolts, around about 2 divisions, and then you can see the op amp recovering there and stabilizing. And of course that was with the 1 microfarad output capacitance. Let's try it again with the 47 microfarad, and there we go. We've got a whole bunch of noise this time, but the transient's not as large as before. Let's try that again. There we go. So it's a little bit smaller than before. Now set my output to maximum here and it should be 5.5 volts, but it's not. And once again, another trap for young players. It depends on where you actually measure that voltage. I've got the ground reference over here on this side of the load, but I'm actually I'm actually measuring the load voltage right on that resistor there. Now, the problem with that is that the burden voltage of my multimeter is in place there, plus the voltage drop in the wiring and the breadboard and stuff like that. So if I disconnect that, yeah, it's a little bit hot, and I connect it straight onto the tab of my TO220 device, I think we'll find it's exactly 5.5 volts. Bang! There it is. So that drop is in your breadboard and your wiring and your burden voltage. Just be careful. Okay, I've replaced the current shunt resistor with just a jumper link to get us greater output current capability. I've currently got it set to just over an amp, and there's our output noise. Not a problem at all. We're still getting 5.48 volts out maximum, and I can wind that wick up a bit. Of course, things are starting to warm up a tad now, and it is rated to this, but now we're going a bit over. We're starting to see some funny business now, are we? Maybe the thermal overload's kicking. Oh, something's kicking in, perhaps. Yeah, there we go. Our output's dropped to 2 volts. It's dropped out. Bang. But there you go. It actually recovers at 1.2 amps. Not a problem. I like it. And just for fun, we'll measure that heatsink temperature. Will be at the 1 amp. It's about 28.5, 29 degrees ambient here in the lab, and let's probe that case and see what it's at. Okay, it looks like it's settling at about 43.5 degrees. And the heatsink itself is at about 41.5 degrees C. So there you have it. There's some basic, really rough and ready tests, not sort of really precision power supply measurements at all, but I think it passed with flying colours on the breadboard. It pretty much worked as expected. I'm happy with that, so I might have to get on to laying out the board and building this thing up for the final project, and I'll eventually show that one. So I guess it's to be continued, and there might be some more performance checks and other things on this, but anyway, hope you enjoyed that. See you next time.